just focus on sodium and potassium. If this is my membrane now, and this is the extracellular fluid out here, this is the intracellular fluid on the inside, I can say it looks like this, right? Here's my outside positive, here's my inside more negative, or less positive, right? This means less positive also, right? And this is a non-polar membrane in the middle, right? Hydrophobic. We mentioned the other day that anything that has a charge, can it pass through the phospholipid bilayer? No. So if it's there, it's going to stay there. If this is here, it's going to stay here. This membrane now has potential, right? This system, this is a cell right here, this system now has potential. We have separated charges of opposite sign by a barrier. And if I were to hook a voltmeter up to this, it's going to measure volts and it's going to measure 70 millivolts. Now, does every cell that have potential, is it exactly 70 millivolts? No. Some are 90, some are 60. It depends on the exact cell we're talking about. The only cells that are capable of generating potential that we can use to make current are two kinds. Neurons, which is what we're focusing on here, but also muscles. So muscle cells, both cardiac, skeletal, smooth, can generate electrical potential. So they have a membrane that has potential. Neurons have membranes that have potential. There are other examples, but those are the two big categories. So that's going to have potential like that. Now, we want to also denote direction here, because that'll become important in a discussion of how the electricity flows. How do we get current? Here we've got an intracellular side and an extracellular side of the membrane, right? And generally speaking in biology, whenever we define something that's referring to a cell, it's always with reference to the cell, not what's outside the cell. Does that kind of make sense? So if I want to define direction of this charge, I want to define it relative to the cell side of the membrane, not the extracellular side of the membrane. That's just a general kind of way we talk about things. It's always with reference to the cell. Okay. So this charge is 70 millivolts. But we could have had 70 millivolts by having these flipped also, right? We could have the inside positive and the outside negative, still hook it up and have 70 millivolts. So I want to know which do I have here. So I want to say, the way to say it is this, is that the potential difference across the cell membrane is 70 millivolts, and the inside is negative relative to the outside. So we often talk about potential being a minus 70 millivolts, but that doesn't mean 70 millivolts below zero. I don't think that's even possible. Okay. It means the way to read this is that the potential of a neuron cell membrane is 70 millivolts, the inside is negative relative to the outside. What if I tell you tell me how you read this? What if I tell you that's now the membrane potential? How do you read that? Positive 30 millivolts, and what does it really mean? It means the potential is what? 30 millivolts, and the inside is positive relative to the outside, or the inside is more positive. Is that okay with that? How would you read this? Yeah. The potential is 90 millivolts, the inside is negative relative to the outside. Or the inside's, you could also say the inside's more negative, the inside's less positive, or something, right? But that's what we're wanting to imply. Okay? You all right with that? That concept okay? Now at rest, if a neuron, let's focus on neurons. If a neuron is not conducting any electricity, it has a resting membrane potential. So nothing's happening. This is what's established by the combination of all of these ions here being pumped where they're supposed to be pumped. And we get at rest, we get a resting membrane potential. And the resting potential, or the resting membrane potential, of a typical multipolar neuron is minus 70 millivolts. Which means that the potential difference of ions across the cell membrane generates a potential of 70 millivolts. The inside is negative relative to the outside. Okay with that? Communication is going to be when that changes. A cell is going to know, so to speak, that something's happening or it needs to do something when this number changes. Because this is what it's like when nothing's going on. If we change it, something's going to happen. Now this can only change two ways. Right? It can become what? It can get more negative. How about let's just say it this way. It can become more negative or less negative. Which this also means less positive, and this also means more positive. Right? Does that make sense? But I want to focus just on this because we got a negative here to start with. Now, if something becomes more negative, okay, you know the word the polar? Polar just means different, right? Like the north and the poles of the Earth, the north and the south pole. It just means that the two ends are different. This membrane is polar, right? Or I don't want to use polar in the sense of the chemistry word, but let's do it this way. This membrane has polarity, right? This side of it looks different than this side of it. Yeah, you'll believe me on that one? So this shows polarity. Right? If it becomes more negative, so if this number goes, let's say, from minus 70 millivolts to minus 85 millivolts, the inside got more negative, right? We could say what's happening to the difference here? Is the difference here getting greater or lesser? Greater, right? As the inside becomes more negative, we're making the difference between the two sides bigger, right? So the word, the prefix that means excess that we always use is hyper. And we're referring to the fact that this is different. So what have I done to the cell membrane? I have hyperpolarized it, right? Does that make sense? Because it got more different. I hyperpolarized it. Okay with that terminology? It's just a terminology.